intermolecular forces are the attractive forces between the molecules, and they come in different strengths. So we've looked at the London dispersion force, which is the weakest of the intermolecular forces. So it's kind of like the Elmer's glue of intermolecular attractions. It's a weak attractive force. It only results in nonpolar molecules or noble gas atoms. And it's just that usually those types of particles don't have substantial regions of charge. But because the electrons can always move in their orbitals, if by chance that movement of electrons creates a region where there's more electrons and a region where there's less electrons, we can create these temporary partial positive and partial negative regions. Well, if you line up a bunch of these molecules, then they'll line up so that opposite regions attract. Well, the second type of intermolecular force is called a dipole attraction. Dipole attractions or dipole forces are for polar molecules. So the last one, the London force, was for a nonpolar molecule that does not have a substantial region of charge. But polar molecules do. They have permanent partial positive and partial negative ends from the unequal sharing of electrons within the bonds. And so an example might be in this iodine monochloride molecule. Okay, so I think about the electronegativity of iodine versus chlorine. And we know that fluorine has the highest electronegativity of all elements on the periodic table. Fluorine is small, he's got 7 valence electrons, he really wants to pull in more electrons. As you move up toward fluorine, electronegativity also increases. So chlorine and iodine are both in the same group, they're all halogens, but chlorine is going to be a little smaller, so the nucleus is going to have a stronger attraction for its own electrons and a stronger attraction then for neighboring electrons, such as those in the bond between iodine and chlorine. So just because of electronegativity, this is a polar bond. And it's the only bond in the molecule. And so because the chlorine has the higher electronegativity, I'm going to make a note of that. Chlorine, higher electronegativity. That's why chlorine has this partial negative charge. I mean, I could draw the dot structure, and it's a pretty simple one. They're both halogens, so they'll have 7 valence electrons, and I'll purposely line up the single dots, 7, and then boom, link them up. It's just that in reality, because the chlorine has a higher electronegativity for life, and chlorine will always have a higher electronegativity than iodine. This electron pair that's shared will always be pulled closer to the chlorine. And that's why the chlorine is slightly negative. And because the electrons will be lacking from the iodine end of the molecule, iodine becomes partially positive. Okay, so I mean, this is really the same concept that we were talking about then with the London dispersion force. Let's say you got a bunch of these molecules, and you'll always find a partial positive on the iodine and a partial negative on the chlorine. Well, these molecules are going to line up so that opposites attract. And so you'll always get this attraction right in here. So the attraction is right in the middle there. It's between the negative chlorine end of one molecule and the positive iodine end of another molecule. So there's going to be attraction in between the molecules. That attractive force in between the molecules. I mean, down here they're trying to show it with these dots. Those dots represent the dipole force or the dipole attraction. It's an attractive force between the molecules. Oh, and look at how all of these molecules are arranged. They're arranged so that opposites attract. Every time there's a purple iodine that's partially positive, it's organized in a way so that it's close to a partially negative green chlorine end of a neighboring molecule. That's the dipole force. It's the attraction between polar molecules. And it's stronger than a London force because this whole partial positive, partial negative thing is permanent. It's for life. It's not like those nonpolar molecules where, well, 99% of the time, the electrons are equally distributed between the two atoms, and maybe just by random chance, the electrons have moved in a way that puts them closer to one atom versus another. But this was temporary. So these little partial positives and partial negatives just don't last that long. This is permanent. These are molecules that will always be polar. And so you'll always have these partial positive and partial negative regions, and they'll always then have molecules organized so that opposites attract. So if I'm thinking about like glue, if the London force is like the Elmer's glue of intermolecular forces, this is a little more strong. This is maybe like a hot glue or something like that. It's that little stronger intermolecular glue. I think it even mentions here that because this is a little bit stronger, it's maybe more commonly found in solids and liquids, whereas the London force is more commonly referred to when we're looking at gases, because it's a weak attractive force. It could still be with some gases, but maybe more often I think about these attractive forces with liquids and solids. So let's try question 21. Predict what type of van der Waals attractions. Van der Waals attraction is just a fancy word for intermolecular force. Intermolecular force. Sometimes we can even abbreviate. If you want to abbreviate, it's commonly just referred to as an IMF in the chemical world. If you ever just write IMF, we know that you mean intermolecular force. Okay, what type of intermolecular force occurs between these types of molecules? Okay, so I've got oxygen, sulfur dichloride, and CH4, which would be methane. Okay, so the first thing you're going to want to do is draw the dot structure, which is why we mastered drawing the dot structures. So I'm going to draw the oxygen. I'm getting pretty good at these. There's 6 valence electrons, and I'm going to kind of line up the singles, and it looks to me like I can make a double bond. Fantastic. All right, there's my oxygen, and maybe you knew that. Maybe you're like, oh gosh, I've drawn this a bazillion times. I just know that it's a double bond between the 2 oxygens. Cool, totally fine. Sulfur dichloride. Sulfur is right under oxygen, so it also has 6 valence electrons. And then perfect, I've got 2 chlorine. So I'll purposely link up the singles. Chlorine's got 7 valence electrons. I'll single bond, and I bet we'll do another single bond on the bottom. And then here's his other valence electrons. Sweet. And then CH4. Gosh, these are so great. Maybe because they're easy, right? 3, 4. I got 4 hydrogen to hook on. Fantastic. I got 4 spots. And 3. Whoa, get out of there. And 4. Got it. Okay, so first step, draw the dot structure. Second order of business, we want to label these as polar or nonpolar molecules. Overall, are they polar or nonpolar molecules? Well, you look at the O2 oxygen, and it's really just going to be kind of linear. There's no other way to connect two atoms but with a line. So if I wanted to, I could even put the shape in. And because it's the same two atoms, they're going to have the same electronegativity. They're going to pull on the electrons the same. For the most part, those electrons should share equally between the two oxygens, and this would be a non-polar molecule. Okay, well now we can label the type of intermolecular force. Non-polar molecules that do not have a substantial region of charge should be connected by those London dispersion forces. London dispersion forces. From just the chance that those 4 electrons shared between the two oxygen, maybe they're just kind of moving around in their orbitals, and for a split second in time, they're not equally distributed between the two oxygen. And that would create a temporary region of charge. All right, so let's look at the sulfur dichloride. Okay, so brother, there's 4 groups of electrons on my central sulfur. That makes me think tetrahedron. So there's the 2 bonding groups, and there's the 2 lone pairs. It makes me think about a tetrahedron where there's an atom in the middle. 1, 2, 3, 4. It's 3-dimensional. It's not flat. I'm thinking about that little tetrahedral rocket ship. But 2 of the spots aren't really atoms. So if I take off 2, sorry, you're not really an atom. It's really like saying those other spots, that's where the lone pairs are. There's a lone pair here and a lone pair down there. Do you remember this shape? This is bent. This is bent, where you've got 2 atoms, which would make you think linear, but linear is if there's only 2 groups of electrons that repel 180 degrees apart. Now I've got 4 regions of repulsion, but they're not all atoms. So those extra electron pairs change it from being linear to bent. And bent molecules do not have an equal arrangement around the center, and they're always polar. I think we mentioned that whenever you draw the structure, if you've got lone pairs on your central atom, guarantee it's a polar molecule, because that always represents a region where you could have an atom and you don't have an atom. So it'll always be an unequal distribution around the center. It'll always be polar. And polar molecules then should have these dipole forces. Dipole forces. Dipole meaning like 2 poles, or poles, regions of charge. If I look at sulfur versus chlorine, chlorine already has 7 valence electrons. It's got an extra proton, an extra electron. There's going to be a little stronger attraction between the chlorine nucleus and the chlorine electron cloud, meaning chlorine has a little bit higher electronegativity. And so all these electrons are going to be pulled out a little bit closer to the chlorine. So the chlorine end of the molecule is going to become partially negative. And since those electrons are being pulled away from the sulfur region would become partially positive. And so if I have another molecule, it would organize itself so that the positive sulfur region would be attracted to the negative chlorine region of a neighboring molecule. And then finally, we've got our CH4. This guy's got 4 electron regions around the center, and all 4 are bonding. This is the true tetrahedron. It's the perfect tetrahedron. Everybody's going to be at a nice equal angle around the center. Not 90 degrees, but they're all equal angles, right? Here's like my little tetrahedral rocket ship again. Everybody is at about 110 degrees. And because all of the atoms on the outside are the same, it means that all four bonds are going to be pulling on the electrons around carbon to the same degree. So this is my nonpolar tetrahedron. And nonpolar molecules, again, would not really have a substantial region of charge, and they would be just connected by the London dispersion forces. London dispersion forces. By just a random chance, those 8 electrons around the carbon are not equally distributed around the nucleus. We would create a temporary region of charge.